Awesome.
Cool. Well, hello, everyone. Thanks so much for joining us for this webinar. My name is Marek Olszewski. I'm going to kick things off here, and then I'll be handing things over to Kobe and Iran, who will share more about how we're using SNARKs at Celo. But just to, by way of an introduction to Celo, just wanted to say a few words in case you haven't heard of us before. So we are a open platform that makes financial tools accessible to anyone with a mobile phone. And we're specifically focused on the 1.7 billion people out there who are without access to financial services that many of us take for granted. And you may have heard of this mission before, and I think one thing that makes us a little bit in the space is our user research approach. And so we're very, very user research focused. Over the last 1.5 years, we've visited a number of our target companies and performed over 100 very in-depth interviews with our target customers. And we've synthesized a lot of this work and turned that into a number of insights that we've then used to really influence our roadmap. And so throughout this whole process, we learned fairly early on, I would say, that it's difficult to build something that's compelling for our target audience, that by simply building a new wallet or even doing something creative in the smart contract and a layer, we learned pretty early on that we really needed to attack this at a full stack kind of using a full stack approach. And I apologize for the background noise. I don't know if you guys can pick that up, but it's just about gone. And so as I said, we take this full stack approach to building our cryptocurrency. And that means that we have our own layer one, and we've done a lot of work at the smart contract layer all the way up through to the mobile app layer, where we've developed basically a kind of end-to-end experience that can deliver for those target customers that we've interviewed. And so concretely, what does this mean? It means that we have a fork of Ethereum that is running our own BFT-based proof-of-stake consensus protocol. And we did this primarily because our users told us that downloading headers for, say, a light client was generally too data intensive for them. And so, you know, they were very, very careful and monitored very closely their data usage. And so with that in mind, we knew right from the get-go that doing something with proof of work would be quite difficult. And so we built out our own proof-of-stake protocol. Our users also told us that stability was really important for them. And so very early on, we developed our own platform for creating stable assets that are all backed by the same reserve and can be pegged to various kind of fiat currencies out there. And I think crucially, one thing that we've done that's, I think, pretty interesting is that we made it possible to pay for gas using these stable assets. And in fact, any whitelisted ERC equivalent token on our platform. And then our users also told us that they really wanted to use phone numbers as identifiers. They're very comfortable using phone numbers and have been using it for other things. And so we worked really, really hard to give to create, in effect, a decentralized PKI that maps hashes of phone numbers to to public keys, so that people can find each other more easily. And then I think one thing that we're really excited about is we've also created a protocol that's fully decentralized that allows people to participate in verifying these phone numbers in a fully decentralized way. And so people can install this Celo Rewards app and let the protocol send text messages through their mobile phone, and in exchange can earn some rewards, some cryptocurrency. And then finally, in order to build an end user product, it's important to iterate with taking in feedback constantly and making improvements. And doing it to launch is hard, and so we've also built out our own full on-chain governance protocol so that the community can continue to invest in the protocol and make improvements post-launch. And then maybe last but not least, since credit scores are very hard to come by in a lot of our target countries, we're also experimenting with Eigentrust as a mechanism for creating lightweight credit scores and credit histories for our users. In fact, one of the authors of Eigentrust, Sepp Kamvar, is a Celo co-founder, and so it's only natural that we've been experimenting with this. And then finally, on top of all of this, we have our own wallet. It's a light client that abstracts away all of the crypto and gives you kind of a Venmo or kind of PayPal experience, but without sacrificing censorship resistance. And it's really easy to use. If I want to send a payment to someone, I can look them up by phone number just by looking through my contact list. And then very easily with just one more tap, can add a stable amount that you want to send to them, and then just quickly press the send button. And so with literally just a few taps, it's very easy to send stable value to anyone in your contact list. The Light client does all of the work of looking up through this PKI the right wallet address to send the payment to. And I think more interestingly, it's also possible to send payments to people before they sign up. And so here I'm sending Satoshi $18 for brunch. She bought me avocado toast the other day. I don't know if you know this, but Satoshi's a big brunch fan. And she's not yet a Celo user, but I can still send the payment to her where this $18 actually gets held in an escrow smart contract for her to redeem only once she's verified her phone number. And so this is pretty exciting. This is clearly pretty new for the crypto space that has in the past made it obviously a prerequisite to create a public-private key before you can receive any money in a decentralized way. And I should add that this is fully decentralized. And so that's a super quick overview of what we're doing and some of the thinking and research behind what we've done. And so with that, I just wanted to hand it over to Kobe and Iran to dive into how we're using SNARKs.
Hey, all right, let me take control.
And if Linux is causing you trouble, Kobe, I can go on next slide for you if you want.
All right, I tried taking control, but it doesn't seem that I have it. So maybe you should pass on to the next slide.
Sounds good.
All right. So first of all, I am Kobe. I am doing SNARK work in Celo for this ultralight client syncing that we're going to talk about, and for other users. And we see multiple uses for SNARKs in Celo. One of them is to tackle the problem that Marek mentioned, which is how clients which use mobile phones can use a cryptocurrency with little data usage and not have too much burden on their bandwidth. And other things we are planning to use SNARKs for are privacy and some things we are researching. Please continue. All right. So I first want to give an overview of the proof of stake protocol that's used in Celo. I'm going to show a simplified version of it so we can talk about the essentials. So let's get right into it. So it's a practical BFT algorithm in which we have a bunch of validators, validators which are known to each other. Let's say 100. In this example, we have 3. So what happens is that whenever there is a new block to be added to the blockchain, all of the validators receive a block header from one validator, which is a proposer for this block. If the validators agree with this block header, and they agree with the context of what's happening in the POS protocol, they sign it. Eventually, they send the signatures to this proposer, and the proposer collects all of the signatures together. Now, if there are enough signatures that pass a threshold, essentially, if it's 100, that will be 2/3, so it's 66 validators. If we have enough signatures to pass the threshold, then we will be able to convince anyone that this block header was approved by the validators of the network. So the proposer collects the block header, the signatures on this block header, and broadcasts it outside, and then it moves on to the next proposer and continues for the next block. So what we already see here is that this might be heavy because the block header, let's say, this is something we can't get rid of, but we have a bunch of signatures here, and signatures are not always that small. So we might want to try to solve it. There is another thing that is very important in this kind of protocol, which is what is the current set of validators that are approved to sign on blocks. And this is something that can change for many reasons, but essentially it can change at some period of time. So every n blocks, there is a validator set update. We call this n blocks period an epoch. Now, this epoch today is once a day, and we need to update the validator set at the end of each day. Just to give some background, all of this logic of what validators are going to be the next validator set and all that, that happens in some smart that's deployed on the Celo network. All right. So if you look at some visual description of how this looks like, at epoch 0, which is Genesis block, I guess, or something a bit after that, we have a block header, we have the current validator set, we have a bunch of signatures. All right, and then we create n blocks, we reach the end of the day, and then we say which are the added validators and the removed validators, and now we sign what is the new validator set. So we do that at the last block of each epoch. So this happens every n blocks. Maybe it's important to note that something I forgot to mention, that each block comes at a very fast pace. It's seconds, it's not minutes. So that's something to be aware of. And the last block of each epoch is one out of many blocks. Right. So the first question we can, like the most important question we can ask ourselves now, because this happens quite a lot, we have a lot of blocks. Can we somehow make syncing use less data? That would help a lot to people that want to catch up to the blockchain. So that's a big question we have. So the first thing we look at is something called BLS signatures. And BLS signatures are a very nice and elegant construct that's based on pairing-friendly elliptic curves. And that's something that allows you to take a bunch of signatures that people sign with their own public keys. So, and then you can aggregate them into a single signature non-interactively. So what it means in the context of TBFT, the proposer gets all the signatures from the different validators. So now the validator has, let's say, 67 signatures. So what she can do now, she can take these signatures and aggregate them without the help of any of the other validators into a single aggregated signature that would still verify that we have a signature from a bunch of validators on a block header. One additional thing that we need to add here is what we call a bitmap, which is, we have a list of 100 validators at each epoch. These are the approved validators. But not all of them have to sign at each block. So the bitmap says which are the validators that sign. So it must be more than 66, but it doesn't have to be 100. All right. So before we move on to SNARKs, we can already notice that we already, by using BLS signatures, we already reduced the data by quite a bit. Because now instead of a bunch of signatures, one. So maybe the signature is a bit bigger by a few bytes, but we have just one of it. So that's a really good trade-off. So then we ask ourselves, can we make syncing use even less data? Why not save more? Why not make it even more efficient? So that's where SNARKs come in. All right, so SNARKs are, if you probably heard quite a bit about it from the other workshops that happened in the challenge. I will describe it in a very direct and simple way to set the terminology. SNARKs are, if you look at the acronym, it's a succinct non-interactive argument of knowledge. And there are many resources that you can read on zkp.science. That's a collection of good resources of all the work that happened in the last year regarding SNARKs. Right. So what are SNARKs? Let's look at the simple version of the definition. Given a statement X, a public statement X, I know a witness, which is private. It doesn't have to be shared, such that some relation holds. So what does that mean? That means that we have two actors in the system. We have a prover, which has solution to this problem. They have X, which is the problem definition, and the witness, which is the solution. And what they can do, they can generate a proof that would convince any verifier that the prover had a problem to this solution without having access to this witness. This is the general concept. Verifiers can be many. It doesn't have to be just one verifier. It's not one-to-one. So once a prover generates a proof, any verifier can verify it. All right, let's move on to the next slide. All right, so let's take a concrete example. This would be our statement. Or let's actually talk in this terminal. So we describe a problem. I want to prove that I know X such that X to the 5th power plus 5X plus 3 is equal 45. So this is a very hard problem that's very important to the verifiers in the network. And they really want to know that someone knows a solution. So the prover takes the solution too. And does all of this SNARK magic in the background. It's quite computationally intensive, and generates a constant size proof, very small, a few hundred bytes, that convinces any verifier that there is actually a solution to this problem, and that the prover knows it. So they don't know what's the solution, they know the solution, and that the prover actually knew it. All right, so that's a very simple example. Now, let's look at something that stretches the benefits of it a bit more. So let's say that the verifier cares that this equation, this multivariate equation, holds for many distinct pairs, for 1 million distinct pairs. But the verifier doesn't really care what are the solutions. They just really want to know there are at least 1 million. So if the simplest way the prover could show that to the verifier, let's say that the solutions are not secret, it doesn't reveal anything secret. So the prover could obviously just send the solutions to the verifier. But that would require the verifier to do, one, a lot of work, and second, to get a lot of data to check that. So what the prover can do, they can do on their side, they can generate this SNARK proof to show that they know 1 million distinct pairs that solve this multivariate equation. And the verifier can see that it actually holds. So that's something that already may give you a hint of why it can be used to transfer less data in some cases. Just a hint. All right, so let's move on. So SNARKs are succinct. So what that means, I mentioned it a bit before, that means that the solution, this proof, is of constant size, kind of. It is of constant size, it's hundreds of bytes. It can also be private in the sense that it can also be zero knowledge. If we care about privacy in our problems, we can also make the SNARK not reveal anything about the solutions that we had to the verifier. The verifier knows that we know a solution, but they don't know which. In our case, you will see that we care less about zero knowledge for the ultralight thing. But that's something that's very useful for SNARKs, and that's where SNARKs are in production today in the zk blockchain, which uses zk-SNARKs, zero knowledge SNARKs. All right. So I'll pass the microphone to Elan to tell you a bit more about SNARKs and zk-proof standardization effort.
Thank you, Kobe. I'm Eran Tomer. I advise Celo on the use of SNARKs and other cryptographic machinery. And I'm also deeply involved in the research of SNARKs, having been fortunate enough to have come up with the acronym back at the time and having authored several of the prototypes that use it. And many of you are probably familiar with SNARKs in the context of Zcash, where the privacy, zero-knowledge aspects of SNARK are used. But actually, the original motivation for SNARKs, as we originally studied them, were their succinctness properties. The fact that you can outsource computation to someone that you don't trust and have them send a few hundred bytes that prove the correctness of the computation, regardless of how long it originally took. And this means, in our context, that you can summarize a claim about the integrity of the blockchain very succinctly in a few hundred bytes. As Kobe mentioned, this leads to a bandwidth reduction that's especially crucial when you're dealing with users who are very bandwidth limited. Celo's mission of empowering the unbanked worldwide runs into the realities of very spotty and expensive cell phone service, internet service in much of the world. And so just sending blockchain data willy-nilly, things that maybe we can afford on high bandwidth plans in the developed world, this doesn't work when someone is counting the bytes, really. Using SNARKs allows us to attest to the integrity and the correct structure, in this case, the correct evolution, and the validator's consensus rule of the whole history very succinctly. For those of you who are familiar with Coda, they also use SNARKs for similar purposes, more aggressively with a different trade-off and heavier machinery. For those who are familiar with Fly Client, that's sort of a way to check integrity of blocks in the proof of work setting. And you can think of what Celo is doing as something that is in between, trying to work with proof of stake and trying to build trust in the correct evolution of the chain, but while keeping the cryptography relatively simple and straightforward to understand and verify. Now, all of these builds on the state-of-the-art in zero-knowledge proving systems, and in particular succinct non-interactive ones, that is SNARKs. And this is one of many applications for such SNARKs that have come up in recent years. So one of the efforts that we have in order to help people use the state-of-the-art SNARKs and use them correctly is the zk-proof standardization effort. This is a process that has been happening for the past couple of years, over several workshops with hundreds of participants. And basically, we have people from all over academia and industry, the producers and consumers of zero-knowledge technology, convening to create a community reference document with best practices and guidance, various standards for interoperability, and means for people to plug in applications out of different zero-knowledge building blocks, including the cryptographic schemes, the compilers for compiling statements into the requisite algebraic circuits, and also tools for deployment, benchmarking, and everything else that needs to be done in order to achieve interoperability between the practitioners. If you care about zero-knowledge proofs and SNARKs, then I encourage you to go to zkproof.org and catch up on the proceedings from the past discussions and see how you can get involved in that. Also, so far, Kobe and I have provided some context, but we would be very happy to make this an interactive discussion. Please make liberal use of the Zoom text chat feature, and we'll respond as soon as we can.
All right, thanks, Alan. And yeah, I totally agree. Please ask questions. That would be great. All right, so now we can actually get to how we use SNARKs in Celo. So what our aim is to make the sync faster. So let's start with a strawman example of how we could maybe make the sync use SNARKs. Maybe not faster, but use SNARKs. All right, so reminding you a bit, we have epochs. Epochs are a collection of some blocks. An epoch ends at each day. And at the end of each epoch, we know what validators have been added to the current validator set, which validators have been removed. So this validator set at epoch n, and given some data of which validators were added and removed, we can construct the validator set at epoch n+1. So instead of doing that directly and having clients verify that by themselves, what we can do is to create a snark that shows them the current validator set, the new validator set, and a proof that this transition happened correctly. All right. So just to give a visual description of how this looks like, we have in epoch n, we have the block header. We always have a block header. We have the current validator set. But we also have some data, this additional data, which is the new validator set and the signature on all of these things. The prover can take this set of data. Some of it has to be shared with the verifiers, with the clients as well. And this would be the block header and the current validator set. But we don't have to share the changes in the validator set. What is the difference between the current and the new one that's going to be generated? And we don't have to share the signature, because the prover can take the current validator set. They can take the set of public keys that they have, and inside the snark, the prover can reconstruct what is the new validator set from the diff and the current validator set, and verify there are enough signatures, or more correctly, that the aggregated signature corresponds to an aggregated signatures from enough validators. So the prover takes this set of data and create a proof out of it that shows what would be the new validator set at epoch n+1. So what the clients receive eventually is epoch n data, the block header and validator set at epoch n, and the epoch n+1 data, which is the block header, the new validator set, and a succinct proof, a very small proof that this is actually correct. The transition between the epochs happened correctly. So this, I call this an example because if I'm being totally honest, we shouldn't do that for one epoch, because the succinct proof and the verification of the proofs might be on the same order of magnitude as just verifying the aggregated signatures. So let's move on to the next slide. So what we actually want to do is to to take a bunch of epochs and show that the transition from epoch n to the epoch n plus m happened correctly. Because then we could have one proof which is hundreds of bytes, and prove that the set of changes to the validator set was applied correctly through m epochs. So let's see how that looks like. So similarly to before, we have the epoch that we're starting with, which is epoch n. We have the same data as before, the block header, the current validator set, the changes to the validator set, the aggregated signature. But we also have more private data, more yellow data. And this would be all the epochs between n and n plus m excluding. So we have all of the blocks in between. We have the changes that happened at the end of these epochs. We have the signatures on these changes. And we take these transitions and we apply all of these transitions inside a single SNARK proof. And eventually we get the validator set epoch n plus m together with the proof, and that this happened correctly. So this already compresses the amount of data, or reduces more correctly, the amount of data that has to be transferred to a client in order for them to know the validator set at any given epoch. So you can start from the Genesis block and you can do it in jumps of m epochs, where m can be large depending on some numbers that we're going to get into. And be certain that currently you're following the correct chain with the correct validators that put the right stake and did the right deposits, and you can be certain that you know what you should trust. Right, so let's move on to the next slide. So how do we do that? What are the tools that we use? So we do a lot of this work, specifically the SNARK work in Rust. And we do that using the zk-SNARKs library. And we have to use some constructs that have been introduced in the zk paper, which are listed here. I'll give a brief overview on some of them. So we have the curve that we have an elliptic curve on which we do BLS signatures, and these are the signatures that happen in each block even. So these BLS signatures allow us to aggregate signatures into one signature, and we use a curve called BLS 12-377. So that's one component that we use. Another component that we use is a SNARK curve, which is of type clock-speed curve, which has BLS 12-377 embedded inside it. So what does that mean? It means that on the SNARK curve we can run many different operations on the BLS curve. So essentially, this is what allows us to verify BLS signatures inside the SNARK. So we have like this chain of curves, and we have a SNARK curve, which embeds the BLS 12-377 curve. Another thing which is important to do in SNARKs, some of you might know that to program SNARKs, you don't use normal languages like C, you don't use Python. And actually the computational model is a bit different, or the program model. You use something called arithmetic circuits. So some things which are very efficient to do in, let's say, real-world computers, like SHA-256 hashes, are quite intensive when run inside a SNARK. So another thing we do is we use SNARK-friendly cryptographic primitives. So in order to do that, we use another curve, which is of type twisted Edwards. And specifically, we use Pedersen hashes. And in some point, we use Blake to S hashes. And for those of you who are interested in the details, this is used in the BLS signature phase, where we're taking the message that we're signing. Let's say in our case, it would be the validator set changes. And we want to sign them using BLS, so we have to hash them first, and we have to hash them into an elliptic curve group. So that's something that needs this kind of hash construction, this composite hash construction. All right, let's move on. All right, so we're planning to release some of these tools or constructs that we've worked on soon. Specifically, the BLS signatures part in the way we use them. And to reach the conclusion of what it gets us, we use BLS signature aggregation. That already reduced the bandwidth quite a lot. We have a bunch of blocks at each epoch that already reduces the bandwidth. And we furthermore use SNARKs to take the epochs, a large block of epochs, and reduce the bandwidth even further. So we expect at least 2 or 3 orders of magnitude improvement. And to give some numbers of what this looks like, we can look at the next slide. So really conservative estimates inside the SNARK. This is still work in progress of what it would entail. So a single epoch update would be around 400,000 constraints. These are, let's say, the equivalent of steps in a normal computer program, which is about 75 seconds to prove for a prover. The verifier doesn't pay this cost. It happens in milliseconds. But the prover spends this time. The zk curves that we use support up to 2 to the 46 constraints. So we can stuff quite a bit of epochs inside that SNARK. Of course, there are many considerations to do that. Maybe you need 10 terabytes of RAM to reach 2 to the 46, but so we won't get to 2 to the 46, but we'll get to some good number. And we have a bunch of optimizations in mind in order to reduce the computational cost even further. So if you do a little calculation in your head, I think you get to 1,000 epochs in 4 hours. So that means 3 years, something like that, in a proof of 4 hours. But that's just a silly linear benchmark. All right. So I think we don't have more slides. Let me see. Right. All right. So this is what I had to tell you. And feel free to ask questions or ask for clarifications for anything. And thanks for listening.
Cool. Thanks, Kobe and Eran. Any questions from anyone? No questions. Either the content was too technical or too simple. Okay,
We have one.
2 questions.
Right. So the question is, if only epoch n plus m is committed to the chain, what guarantees are given to intermediary blocks and to intermediary epochs? So that's a good question, because all of the epochs are written to the chain. The chain itself has all of the data. The actors that care about the SNARKs are the verifiers, the clients, the live clients, which want to sync up to the chain, to the head of the chain fast. So the proofs are used by them to be certain what is the current validator set at the head of the chain. But the chain itself contains all the data.
So yeah, I just want to add, so this is assuming, we're assuming here that every epoch has had an honest majority of 2/3. And then under that assumption, this is the assumption we're making for this light client, then if the SNARK shows you have this sequence of signatures that keeps changing the validator set, then it implies that this is really the committee for the n plus m epoch.
Right, thanks, Ayad.
Okay, we have another question from Bernard on how does a verifier use pi to verify the answer? So how does it?
Oh, Ran, do you want to take it?
So the SNARK proof system has a verification algorithm that accepts the statement that is being claimed and the proof that is supposed to support that claim. That is what we denote here by pi. Now there is a generic mechanism for doing this verification. That is part of the cryptographic mechanism of the SNARK. And there are various ways to implement it. The state-of-the-art is SNARK construction that use quadratic arithmetic programs to convey the statement as solutions to certain equations, and the pi would show that such a solution existed and is known to the sender. This is something that is normally encapsulated the cryptographic backend, so to speak, that the application is using. Now, the other part, which is application dependent, and which is what Kobe has been focusing on, is that specification of exactly what it is that we are trying to prove, what is the statement. And in this case, the statement would consist of checking the BLS signature and various other rules that relate to the consensus algorithm of the Celo blockchain. Now, this needs to be precisely specified. It's taking the Celo consensus rules and extracting the portions of them that need to be verified. And then it needs to be expressed in a way that is translated down to that system of equations that ends up being plugged into the backend. All of this is nuanced. It has many considerations, especially when you want to minimize the size of these equations, the constraint system, and therefore make the proving as efficient as possible. So I don't think we'll have time to go into the specifics of how it's done, but if you have specific questions or concerns, we can drill into those.
Looks like we have a follow-up question asking about the verifiers and whether they need to be in the trusted setup.
So let me take that one. So another thing that characterizes the state-of-the-art succinct zero-knowledge proof systems is that they require some pre-processing to create proving and verification parameters, which can be done in the form of trusted setup, just trusting a single party. or in the form of a multi-party computation that creates public parameters that are used by anyone. The fact that the proofs are convincing relies on the correct generation of these parameters in that initial, say, multi-party computation step. Now, the people who participate in that initial step don't need to be, they normally would not be the people who are doing the eventual verification. Rather, anyone can join the network later and do their own verification using the public parameters that are already been posted. But it does require a trust in the fact that when those public parameters were initially created during the multi-party computation, then at least one of the participants in that initial multi-party computation was indeed honest and uncompromised. There are alternatives. There are ways to reduce this trust by using SNARKs that have only public coin initial setup, or SNARKs that support an update of those public parameters, or SNARK that suppose a prudent verification mode that does not rely on the trusted setup. And all of these are matter of active research. But note that in our case, this trust is not essential for the integrity of the blockchain, because it is only used by the light clients. If there is any doubt about the integrity of those proofs, if those proofs are even hypothetically found to be completely worthless because the trusted setup has been compromised, or the cryptography turned out to be all wrong, even in that case, all this means is that the light clients will be less efficient and will have to download more data for their verification until the problem is resolved. But there is still the ability to verify things without relying on the integrity of the SNARKs by downloading the whole blockchain and verifying the block headers and even the full transactions. So unlike in some other schemes, in this case, the so-called trust is only for performance rather than for the long-term integrity.
Actually, the chain would just reject lying proofs. The validators, they can verify as well proof before including it.
The validators indeed make sure that that proofs posted on the chain indeed verify. So in that sense, there is the ongoing check. I think the question by Bernard was proofs are turn out to not be convincing because of a cryptographic failure. And the point is that even in this case, you can still recover and maybe regenerate the proofs for the benefit of future light clients. For those who are familiar with the Shark work that my colleagues and I are doing, it's kind of analogous functionality, but it is at the application layer rather than the SNARK backend layer.
Okay, we're coming up on an hour here. Hey, thank you guys so much. This was a fantastic presentation. Where can all of the participants find out more about Celo and all the work that you guys are doing?
Yeah, and so please visit us on celo.org. We have a bunch of content there, as well as a fairly active Medium that I encourage you to visit. And then keep an eye out for more news from us. Next month, we will be sharing a lot more of our work at that time.
Awesome. Let us know and we'll be sure to update everyone. And yeah, thank you again so much. I'll be sure to share the video with you once it's up on YouTube.
Awesome. Cool. Thanks, everyone.
Thanks, everyone.
Bye.